Recording in progress. So, firstly, can anyone confirm if I am audible and the screen is visible? Hello? Hello? Am I audible?
Yeah.
Okay. Okay. So, can you see my screen?
Yeah.
Okay. So, today let's start with very classic problem. Find the number of positive integral solutions.
Summation k minus 1 choose to k runs from 3 to 15.
Okay. So, uh, there are a few things here. So, firstly, let's try to count the number of possible non-negative integers such that this happens. So, what is that? So, there is that famous way of solving this by using the balls and sticks. The answer is 15 plus 2 is 2, right? If we want to find non-negative solutions. If it's n, then it's n plus 2 is 2. Now, if we just change the non-negative condition to positive, what do we do? What do we do, anyone?
We can substitute.
Exactly. So we just substitute the variables. So this part is clear to everyone, right? This should be clear by now. This is a very basic result information. So now if we change the constraint to positive, what we do is we change the variables and we write the equation as this. Now you see, now what we need to find is we need to find non-negative solutions for this x minus 1, x2 minus 1, and x3 minus 1. So it returns to the same problem here. So now n minus 3, that is a new thing here, plus 2 choose 2. This is the answer. That is n minus 1. Okay. So if the constraint was not positive, but xi's are greater than equal to 2, what will you do? You take the variables to be x1 minus 2, x2 minus 2, and x3 minus 2. And that will have the sum n minus 6. So now finding solutions for this condition is same as finding solution for this, where these things are greater than equal to 0. So it's again going back to the same problem here. So now again n minus 6 plus 2. So what we are doing, we know a particular solution to a particular problem. Now there are different variants of the problem. We're just trying to go back to the problem we knew and then trying to figure out the solution from that solution that we have. So these are like the variants of the same idea. Now we change another thing. We change the equality to some inequality. So as someone pointed out, you can also do by taking cases. So what you can do is this expression x1 plus x2 plus x3 less than equal to 15. This can be like divided into 15 expressions. That is x1 plus x2 plus x3 is equal to 1. It can't be equal to 1. All of them are positive integers. So x1 is greater than equal to 1, x2 is greater than equal to 1, x3 is also greater than equal to 1. So this can be this must be at least 3. Before 3, there is a solution for it. And then again, you look for the sum to be equal to 4 and 2. Now you count the solutions, the number of solutions, right? For this, you can count. For this, you can count. The sum. Okay. So that what we will have? What will be the answer? This is 3 minus 3 plus 2 by 2. This is 4 minus 3 plus 2 plus 2. So on to 15 minus 3 plus 2. That is starting from 2 to 2. Going up to 5. Yeah. So that is the answer. Now, I would like to introduce you to some a different method of solving the same problem. That is just by introducing another bin. So essentially what we are looking forward to is another equation, number of solutions for another equation, and the equation is given like this. what are the constraints? X1 is greater than equal to 1, X2 is greater than equal to 1, X3 is greater than equal to 1. What about X4? We write the same thing. Yeah, exactly. So what we want to do is we want to write the same equation in a different form, which is known to us, for which you know how to solve the number of solutions. So X4 here should be greater than equal to 0 because X1 plus X2 plus X3 is less than equal to 15. So this variable is a positive variable. Nice. So now, okay, so we don't have a problem with this, and we know how to change them. So we write the equation like this. And that will give us. And now this must be greater than equal to 0, this must be greater than 0, this also must be greater than 0, this must be greater than 0. So what is the number of solution of this? That is 12 plus 4. 16. I hope I didn't do any calculation mistake here. So this is also the answer, right? So this also must not count the number of ways this can happen. And again, we saw that this also counts the number of ways this can happen. They must be equal, right? So this is called counting in two different ways. I was not going to introduce this now, but okay. So as someone gave another method of solving this, and now we have our method of solving this, where we introduce another variable, which is also sometimes called the slack variable. And now we have the number of ways we can do that. So this must be equal to 16. See, if someone gave you to prove this, now that won't be in terms of 15 or something. It will be in terms of n and k. So just make it x1 till xk is less than equal to n. Xi is equal to 1. So now solve for the number of possible solutions using this method and using next. So this will give you something, some summation form thing in terms of combinatorial n plus k, or what will that be? N minus k plus k minus something. So n minus 1 plus k minus, I guess. And we have to sum on k, I guess. And yeah, and you will get something. And again, if you solve in this the second way, you'll get something which will be a single term. And both of them will be equal because they are the solution of the same problem, but solved into different ways. And so someone can give you to prove that, they will not give you all this. They will just tell you to prove that this is equal to this for any n and k. And then what you can do is just go by binomially, resolving all the terms and see what happens, the factorial cancellation and so on. Or what you can do is you can go back to this problem and write that this is the problem we are working at, and now we go with two different ways. If we solve it like this, we'll get this expression, which is the left-hand side. If we solve it like this, we'll get the right-hand side. And we solve both the things correctly. So the left-hand side must be equal to the right-hand side. Because there is only one answer to one single mathematical problem. So yeah, so that's why they're equals. This is counting twice. So yeah, I hope this is clear.
If it is for general, like there are variables and the sum is n, then for non-negative it's r plus r minus 1 is r, right?
Yeah. That is the fundamental thing, yeah.
This will be 15.
Sorry?
I think this will be.
I can't hear you properly. Maybe there is some problem in the connection. Hello? Go on. I caught you up to that something 15
This will be
choose.
15 choose 4 instead of 16 choose 4.
That will be 15 choose 4. Okay. Where did I go wrong? Yeah, that will be 15 choose 3, right? It's not 4. It shouldn't be 4. It should be 15 choose 3. Yeah. So sorry for this error. There are 4 terms, so we need to introduce 3 more, what you call the sticks. So that should be the thing. So it should be 15 to C. So yeah, so I think yeah. So this should have been corrected earlier. 15 to C. Is it correct now? That is the fundamental thing, right? What is the fundamental thing here? The fundamental thing is x1 till xk equal to n, xi greater than equal to 0. Number of solution is n plus k minus 1 choose k. This is the fundamental thing. Now, whatever equation we have like this, with some other constraints on x's, some other inequality, like not the equality, maybe greater than equal. It shouldn't be greater than equal to, then there is infinite number of solutions. Okay, so there are other things too. Like you can change this thing to greater than equal to, and then constrain xi's to be xi less than equal to 5 or something. That is also a different kind of problem, but on the same area. So you see, so now you have to transform any other problem into this particular method, in this particular version. And now you can apply this formula. So yeah, that should be 15 plus 3. The thing is, combinator is such a huge, like, there are so many different ways of solving problems, and all of them are very important. So, let me just give you another one, which is a very interesting problem, which can be solved in 2 different ways. So there is a n cross n chessboard. Okay, n cross n chessboard. Now, yeah, so on each square there is a lamp. So there is, I don't know how to draw that. It's like a bulb. Okay, there are lamps. Okay, on each square there is a lamp, and they can be turned on and they can be turned off. So the lamp might be on, the lamp might be off. So initially all the lamps are turned off. So when you first get the board, all the lamps are turned off. Now what you can do is, you can touch a particular square. So suppose you decide to touch this square. So what that will do is, touching a particular square will change the state of all the lamps in its row and in its column. So suppose you touch this square, initially all the lamps are turned off. What will that do is turn on all the lamps in its column and in its row. So if you touch this particular box, then in the next step, you will see the board where all the lamps in the first row are turned on. All the lamps in the second column, sorry, the first column is turned on and the second row is turned on completely. and all the other columns, or all the other boxes, and the lamps are turned off. So that is the configuration. If you touch this particular, what is this? Is a first column, second row box. Okay. So that is what now after this, suppose you touch this box. So what will happen? It will again change the state of all the lamps in the second row and the second column. You know? So what will happen is in the next state, you tell me what will be turned on and what will be turned off. Anyone? See, firstly, this will be turned on. This will be turned, like everything on the second column will be turned on because they were turned off, and now they will change the state because we click something on that column. What about them? What about this? This will be turned on and turned off. This will be turned on, right? All this will be turned on because they were turned off. They will change the state. Now, what was this? This was already turned on, right? Okay, sorry. They were all turned on. They were already on. So they will now be off because they were on. So they will now be off. And this was also on. So this will also be off. This was also on. So this will also be off. Very good. And what about them? These were turned on and they will not change the state. So they will remain turned on. Okay. And the other bulbs are turned off. So do you understand now what is happening? Now suppose you click another something here. Okay. It will change the state of this whole row and this whole column. So the bulbs which are turned off will now be on, and the turned on bulbs will now get off. Okay. So this is the process, and this is how the chessboard works and the bulbs. Okay. Now what you have to prove that so firstly all the bulbs are turned off. So you are having a chessboard where all the bulbs are off. Now you have to touch on some boxes so that all the lamps are eventually turned on. So prove that in finite number of touches, all lamps can be turned on. And then the next part and the most important part, find the minimum number of touches.
All lamps are turned off initially.
Yeah. So find the number of touches required to turn on all the bulbs. Okay. Find the least number of touches. And that will depend on n. Obviously, that will depend on n. Depending on n. So first prove that in finite number of touches you can turn on the bulbs, all the bulbs, and then find the least number of touches you need to turn on all the bulbs. So think about the problem very carefully. If we give you the complete solution, there are so many things to learn from this. Okay? This particular solution.
Sir, it is possible in finite number of modes to do it.
Yeah, of course. Yeah. So how will you do it?
Just change the state of every cell. Use the operation on every cell.
Exactly. Use the operation on every cell. Yeah. And why will that do?
Because what happens is that like you have to suppose if you have used, take a certain cell. If you have used like whatever, if on that cell you have applied the operation odd number of times, mark write into that cell number 1. If you have used the operation even number of times on that cell, write 0.
Exactly.
Then
yeah,
the condition becomes so if what is the condition for being a certain cell being turned on at the end is that the addition of the row and the column minus the cell itself should be odd.
yeah, yeah.
So
That's correct.
for that you have to that all cells that works.
Yeah. Okay. So let me just So this is a very key observation. So see, suppose this is the board. Now, what is the condition of this light to remain turned on, to be turned on after whatever? Suppose you do finite touches. After that, this is turned on. What is the necessary and sufficient condition? That is, it must change its state odd number of times because it was initially turned off. So it must change its state odd number of times. Now, how can this change its state? It can change its state only if you have touched something which is on its row or on its column, and not otherwise, right? So eventually you must have touched odd number of bulbs or boxes in this row and this column. So suppose you have touched any 3 boxes here, then this will be turned on. And this is also in that place, you know. So suppose you have touched here, here, and here, then also this will remain turned. You know? So there must be odd number of touches on its row union its column. So what is a row union column of a particular box? That is something of this figure. So this union this included, and so yeah. So now suppose you have touched all the boxes in the square. Then what will happen? Then for any take any box, take any lamp. You have touched all the boxes. So how many boxes you have touched in its row union column? You have touched this, you have touched this, you have touched this, everything you have touched, right? Here also you have touched everything. So total, how many boxes you have touched? You have touched 2n minus 1 boxes, right? Am I right? Here there is n, and now you have count this. So just remove this and count. So n minus 1. So n plus n minus 1, 2n minus 1. So if you have touched all the boxes in its row and its column, then it changed its state 2n minus 1 times. 2n minus 1 is odd, so it's eventually turned on. And that is true for any other box on the chessboard. Start from any other box. If you touch all the squares on its row and its column, it is eventually turned on. So if you touch all the boxes on the chessboard, all the lamps are turned. So in n squared touches, You are done. Doesn't matter what n is. Okay. Now, is n squared the minimum number of touches you need to turn on all the boxes, all the lamps on the chessboard? Is it clear till now? Why n squared touches, like touching all the boxes, will do? See, think if n is odd, what happens? What happens if n is odd? Then do you need n squared touches, or you can do something simpler to turn on the boxes, on the lamps? And just note that this is a crucial fact, and this is always a crucial fact, the only important fact about the problem. That is, a lamp is turned on if you have touched odd number of boxes in the union of its row and column. Think about it.
I think we can do it in n plus 1 by 2. I mean n square plus 1 by 2.
N square plus 1 by 2.
Yeah.
Is that a natural number, first of all?
No, like for odd n.
For odd n. Okay. Okay. Can't you do it n touches? If n is odd, can't we do it in n touches? What about just pressing on a row, on a complete row? Just go and like touch all the boxes in a particular row. Let's say the bottommost row. What will happen after that?
Yes, that does work.
Yeah, that works, right? So if n is odd, just touch the complete bottom row. Okay. So what about the lamps which are not on the first? So suppose what about this lamp? This is changing its state exactly once. So this turned on. So any box above the first row is changing its state exactly once because of the touch on its bottommost row, right? So everything is changing its state at most exactly once. So all are turned on above the row. So there is a problem. Now what about the last row, the bottommost row? So how many times is this changing its state? How many times does a box change? Does a lamp change its state? The number of touches in its row union column. So how many box did we touch in its row union column? We didn't touch any box in its column except this one. How many in its row? N, right? So there are in total n many touches in its row union column, and so there are n many change of states of this lamp. Same here. It's changing its state n times. Now n is, what if n is odd? If n is odd, all these boxes, all these lamps are changing the state odd number of times. So finally they will also be turned off. So the whole square is turned off.
I think I can prove this also.
Will prove what?
Prove that this is the least required for odd.
Exactly. So now, like that's very obvious, right? So can you do it in less than n steps, in less than n touches? Can you, like, even if n is odd, even if n is even, doesn't matter.
Yeah.
In less than n touches, you can't do, right? Because there must be a column or a row where there is none of the thing is touched.
Yeah, that's true.
Right. So by PHP, you can, so just try to think the concrete argument for this. That's why I said all the different things are used in the solution. So look at PHP and try to do it from that angle, and you will see if you have strictly less than n touches, you can't turn on or leave turn on. You can't, there must be one box which you're not changing the state at all. You can't change the state of one box. Some box, like what I'm trying to say is you can't change the state of all the boxes in the board by n minus 1 touch or less than equal to n minus 1 touches. So n is the bare minimum. And now in the case of odd, where n in the n cross n case where n is odd, you can light all the lamps using n many touches. So that's the minimum, and that's a possible way to do it. And we also saw that by n squared touches, you can turn on all the lamps in any chessboard. whether n is odd or n is even. Now, so what is left to show or what is left to think? That is, what about if n is even in a n cross n chessboard? In that case, can we do it with less than n squared touches? That is the thing left. Think about it.
Yeah, that is possible with less than n squared touches, because we can take color a full row and a full column.
Sorry, you can take
one row and one column and color all of them. Sorry, touch all of them, whatever the language we use.
and that will do. No.
I think
So let's do that. Let's see.
And do not touch their intersection.
Okay, so you tell me what to do. So you will touch all of this.
No, that's wrong. That's wrong. Sorry.
It doesn't do, right?
Yeah. I think I can do for the even case.
Yeah. So what is the answer?
So suppose like I can show you a method. Like suppose n is
No. Sorry. Just hold on a second. You can show me a method in how many touches?
in n touches.
In n touches, you're showing a method in one. Okay. Okay. Tell me.
So suppose n is equal to some 2 into n is equal to 2 into some odd. So it is twice an odd.
Okay.
So if it is twice an odd, what happens is suppose like 6 or something like that. Yeah. So twice an
Yeah.
odd. So just color like give me a 6 by 6.
Yeah. So what we'll do after that? How will you call?
Yeah. So like bottom so bottom left 3 will be
Bottom left three by two. Like you are saying something like this.
no bottom left at bottom left corner that is colored. Bottom second then above that it is colored. Above that it is also colored. That is, you do like n by 2, like n by 2 u times color, n by 2.
Okay.
And opposite side you do on the upper half. Opposite side n by 2. Yeah.
Okay.
You touch.
Okay. Yeah. So this will do. If n is two times.
Yeah.
No, this shouldn't be. Wait.
Why sir?
Just hold on a second. You see, how many times is this changing its state?
Okay.
You understood, right?
Yeah.
This changing its states n by 2 plus 1 times. Do you understand why this is happening?
Yeah.
So this is even. Yeah. So the thing is, I will tell you, but this is a nice try. Honestly, this is a nice try. But the thing is, that if n is even, then you can't do it with any less than n square steps, n square touches. So if n is even in an n cross n chessboard like this, you must touch all the boxes in order to light all the lamps. Now try to prove it, why that is the minimum. So, any progress? See, for odd it's done, right? Now the only thing is for if n is even, what to do? How to prove that n square is minimum, or if not minimum, how to find whatever is minimum. So let's see. Okay. So I will define a function. This might seem very weird, but I will define a function from a set S to the set S. Now, what is a set S? It is a set of all possible sets of lamps or boxes on the board. So this is basically the power set. I don't write power set. It's a power set of the chessboard. So if the chessboard is C, what is C? C is the chessboard. So this is the set of all subsets of the chessboard, right? That is basically S. So for example, if this is the n-Gaussian chessboard, then this row is an element of S. This 2 square is an element of S. So any possible combination of or this and this, okay, this and this to discrete. So these two combined is an element of S. So S is the set of all possible sets of lamps. So now how do we define the function? Any guess? So given a set of boxes, what F does is, so this is something, this is say A. So A is what? A is a set of boxes or lamps on the chessboard. So what we do is we click on all the elements of A once. That is, we touch the boxes of A. A is a set of boxes. So we touch the boxes which are on A, like all the A boxes. The boxes. Now that will eventually turn on some lamps and the other lamps will be turned off. So that will give us a configuration of lamps, right? Initially, all the lamps are turned off. Now we touch the lamps, touch the boxes which are consisted in A, and that will turn on few lights. And that is the turn on lights. The on lights will also form a set of boxes. So that will be, let's say, B, which is also an element of S, where S is the set of all possible sets of lamps. Am I clear? Can anyone please confirm? Because I don't know how to explain it in more details, but do you understand what I'm trying to say?
Sir, so you mean that A is a subset of S? A is a subset of the chessboard?
Yeah, A is an element of S and A is a subset of the chessboard. Yeah.
A is a subset of the chessboard. We will turn on, or we will touch every cell of A,
Exactly.
and the set of all cells within the chessboard which have been turned, if lamps have been turned on, those cells are D.
B, yeah, exactly. So we define the function in that way. We map A to B if touching A gives B to be the set of turned on lights. That is the way we define the function. Okay. So for example, suppose this is A. Okay. A is the row. So now what will the function give us? The function will give us something like this. Like, will give us B, where B is all of this and not this. Right? So A will be the bottom row will map to all the set of all boxes except the bottom row. Okay. What will the whole chessboard map? The whole chessboard will map to, again, the whole chessboard, right? What is f of, let's say the chessboard is C, then what is f of C? F of C is C, right? Okay, so I hope this is clear. If there is any doubt, let me know now, because this function will play a very integral part of the proof. So assuming we are on the same page, let's move ahead. Now, what about, okay. So,
Sir, will you use the property that f of A complement equal to f of A? Or
no,
is that
I
true?
don't think that is true. No. F of A complement might not be f of A. F of phi is not f of, see, that is of course not true. F of C complement is phi. F of phi is nothing. F of phi is phi. So anyway, so let's see few things. So firstly, is the function surjective? And there is another question. Okay, and then there's actually the same question. That given a particular box, given a just a particular box, let's say this box, a particular box on chessboard, can we touch some boxes such that only this box is turned on and all the other boxes are off, all the other lamps are off? Can we do that if n is even? So now what we are doing is we are doing on n even. So given any particular box, can we touch a finite number of lamps such that only exactly that box on the chessboard, that single box on the chessboard is on, and all the rest of the boxes are off? We can. How? Just touch this row and this column. What will happen to the board? Tell me. Tell me. What will happen to this? Any box here? How many times is this changing its state? Fast. Now it should be easy, right? If you have spent really some time thinking about it. It's changing its state twice. One from here, another from here. To see how many times it's changing its state, we again look at its row and its column, and there is one on its row which changes, which we have touched, one on its column which we have touched. So it changes state twice. Is it clear? Can anyone please confirm if this makes sense? Okay, no response. So I will just go again. This is, let's say, a box. So is it turned on or turned off if we have touched this row and this column? This is not in that row or that column. So we have to look at its row and its column to see how many times it's changed its state. And in its row and its column, we have two touches. We have touched one on its row, one on its column. So it changes its state twice. And if it changes its state twice, it will remain off. It will remain turned off. Because it's turned on at the first step, and the even number of steps it's turned off again. Because it started with off. So this turned off. Anything here is turned off for the same reason. It changes state twice. Here also it's turned off, here also it's turned off. So if you not worry about the other part of the board. Now what about something here? So this was our target box. Okay, so we are looking at all the other boxes. So what about here? It is changing its state n number of times. Because there is nothing on its column, but there is n number of touches in its row. That is true for any other member of this row, except this intersection. And as n is even, this is also changing its state even number of times. So this is also finally turned off. So everything on its row, except this, is turned off. Now what about on its column? Exactly same thing. It is changing its state n number of times because of the n touches on its column. So it's finally turned off. This is also turned off. Now look at the intersection. How many times is this changing its state? We saw it before also, 2n minus 1 number of times. 2n minus 1, 2n minus 1 is always odd. So this is changing its state odd number of times. So this is finally turned on. So what is happening? So this thing here is a set of boxes. Touching them is leading us to this configuration of lights. Do you understand what is happening? Okay. Take time to understand this, but understand this completely. Okay? And this is exactly saying that this is subjective. So now if we select, and this is not only just turning off, this is not, it's like, see, even number of changing state means not changing its state. So now if we have to add light in a particular box, we know how to do that without affecting any other box of the chessboard. So that implies subjectiveness. Think about it. Given any configuration here, we can just take the compilation of all these individual things and compose them, and that will light that exactly configuration what we need. For any B configuration of boxes here, we have some A, which is the union of all this T-shaped thing for each element in B, and that A will map to B under F. Okay, so if F is surjective, are we done then?
Yes, we are done.
We have done. Why are we done?
Because S and S, the function is from S to S. So both sets have the same finite size. So surjectivity implies also injectivity.
Subjectivity implies injectivity. Exactly. Yeah. So now if it is injective, then?
If it's injective, then it's bijective. So FC equal to C implies F inverse C equal to C. So there is.
So there cannot be any other configuration which leads to C. The whole just. Yeah.
Yeah.
So we don't really need bijective, but yeah, so that's the thing. So this is also another important thing. So if there is a function from a same set to a same set, so subjectivity. So there is a very good way to say it: subjective, injective, bijective. Okay. So let's not say it that way. Yeah. So see, subjective implies bijective here. You know, this is there. Injective also implies bijective here. So injective, subjective implies injective, injective also implies subjective. So maybe I'm just complicating a very simple thing. Whatever. So by subjectiveness here, we really get injectiveness. And now as it is injective, and we know that f of C is C, like touching all the boxes in the chessboard results in lighting all the lamps. That really means that there is no other way to touch some proper subset of the chessboard to light all the lamps. So you necessarily need to touch all the boxes in the chessboard. So this is a beautiful application of functions in combinatorics. Okay. So I'm not sure like how much clear the solution is to everybody, but yeah, this is a long solution, and of course a non-trivial one. but take time to adjust with it. And there is also another solution of the same problem, which doesn't use this function, which is also very beautiful, but I won't discuss it today because I don't have a lot of time. So let's move on to another problem. You can try to figure out the other solution, and I can share it in the group, or yeah, so I can share the other solution to you. So now let's try this one. Students in class form groups. Okay, so there are students and there are groups formed by students. Each group of 3 members. Any two distinct groups, have at most one member in common. So prove that if there are 46 members, like 46 students in a class, 46 students, then prove that there exists a set of greater than equal to 10 students in which no group is properly contained. Is the question clear? There are 40 students and there are groups with 3 members in each group. Okay. And 2 groups can't have more than 1 member in common. So there is at most 1 member in common. So you have to prove that you can manage to pick up 10 students in which there is no group properly contained. Okay, so anything, any progress? Completely clueless, is it? So try to again use of functions. That's very this thing. And okay, so let's take, so let M be the maximal set of students without any group. Okay. Maximal set of students without any group. So what do you mean by maximal? Anyone? What is the meaning of maximal here? What do you think? This is the largest possible set we can have. By that, what I mean is, if you add any other student in this set, it will make it contain another group in it. This is maximal under inclusion of sets. So that is, take all possible sets which satisfies this particular property. What is the property? That there is no group contained in it. There is a proper group contained in it. In that set of students, there is no group of 3 which is in that set of students. So take all such possible sets like that of students. Now, there must be some inclusion chains in that set of all sets, satisfying that condition. So now you take the largest of them that exists because of Zorn's lemma. So that and all I don't want to mention here, but just look it up. Which is equivalent to axiom of choice. And which you fundamentally assume will be that. So all that is not necessary now. So the thing what I'm trying to say is maximal means this M is a set satisfying this particular condition. And if we add any other student in this set, then it will destroy that condition. Okay. And there exists some maximal set like this. Why that is true? That comes from Zorn's lemma. We don't talk about that, but you can assume that it exists. Okay. So now if M is a set like that, then what exactly happens is, take any X, a student, from the set of, so suppose, let's say S is the set of all students. So S minus N. So S is the set of all students. So if X is a student who is not in this M, then if you see, if X, now X is in some group, let's say, so let's XAB be the group of X. Now you see, AB must be in M. This implies is their group. Let's say XAB is their group. Then AB, these two students, must be in M. Why? If they are not in M, then just add X to M. If AB are not in M, add X to M. That will give you another set, and that will not destroy the condition, because including X won't give birth to a new group which is strictly inside that set of students. But that will increase the number of elements in M. But M was maximal, right? So it is not supposed to happen like that. You can't add any other student without destroying the condition. That is the definition of maximal. But here you are adding X, which is increasing the number of students in the set without destroying the condition. That can't happen. So if X is outside M, where M is the maximal set satisfying the condition, then the other two students in the group of X must already be in M. So we define a map from S minus M to M. How? We map X to not exactly M, to pairs in M. To pairs in M. That is M cross M. Not M cross M. It's more like unordered pair. So it's M1, M2, two students. M1, M2 in M is the set of two subsets of M. So X is mapped to AB. So in general, a student here is mapped to the other students in its group, and they must be inside M, because as I said, if not, then you can add the student and that will increase the number of elements in M without destroying the property that it doesn't contain any group. So these two students must be there. So like this, you are considering the map. Okay. And now we have to check that this map is injective. Why is that so? Suppose f of y is equal to f of z. That means what? And y is not equal to z. That means what? That means YAB. So, and suppose this is equal to AB. Then it means that YAB forms a group and ZAB also forms a group. Right? Now, this can't happen. Why this can't happen? Because they have an intersection of more than two students. That is not possible by our given condition. That at most one member in two groups. Right? So this is not possible. So if y is not equal to fz, if y and z are two different students. Okay. And now, okay, and now this is from T minus S.
Sir, one question I had.
Yeah.
Just please go to the previous page.
Sure.
Now, suppose there is a group AC.
Sorry? A, C, and D.
Yeah. Is a group. A, C, and D is a group.
Okay.
Suppose C and D are in M.
Okay.
Suppose C and D are in M.
Yeah.
Now, can you state that A belongs to M?
It doesn't belong to M. If C and D is in M, A must not belong to M.
So, but we have said that A belongs to M. A, B belongs to M.
How?
He has written.
No. If X belongs to S minus M and XAB is a group, then AB belongs to M.
Yeah. So why? Tell me in this condition why ACD is not a group.
I don't understand. Who is A? Who is C? Who is D?
A is what you have taken. A is my A is same as your A.
Okay. A is just a A is something in group. Okay. So A and what is C?
C and D are two elements which are in the same group as A.
Okay. So suppose there is another group ACD.
You understand my question, sir?
Not exactly till now. So you are saying there is another group, which
there
is
ACD. Another group ACD, such that ACD are in the same group, and C and D both belong to M. Is that possible?
That is not possible.
Why is that not possible?
That is not possible because A is already in M. If you have to take all this as hypothesis that X is not in M, and XAB forms a group, and also ACD forms a group, then CD cannot be in M. That is very trivial because A is already in M.
But why is A in M?
Why is A in M? You have
Why?
assumed that X is not in M, right? That
X
is
is
fine.
not in M, right?
You are starting with something which is, you are starting with a student who is not in M.
Huh.
Okay. Now, suppose that student is in a group of 3 students, and suppose that group be XAB. The other 2 students be A and B. Then A and B must be in M, because if not, if A and B are not in M, you can add X to M. You can take this set, M union X, and that will be a set satisfying that condition. What is the condition? That there is no group inside that set. Inside this set of students, there is no formed group inside this set of students.
Okay.
Because there wasn't any formed group in M, and now you are adding X. And to form a group with X, we need A and B. Do you understand? And if A and B, some either A or B
No.
is
So,
not in M.
So I
Yeah.
will change my question. So what if X CD? What if X belongs to 2 groups?
What if X belongs to 2 groups? Okay, fine. Yeah, it can belong to 2 groups.
So suppose another group is X CD.
Then CD also must be M. Must be in M.
Yeah, X CD.
Yeah. If XCD is a group,
CD
this
is
implies CD is in M.
CD is in M. Now,
Yeah.
how can you prove that AB are in M? AB are in M.
AB, for whatever group there is with X, any 2 other member will be in it. I am not saying this is the only group. If XAB forms a group, then AB must be in M. And using the same logic, if XCD forms a group, then CD also must be in M.
But you are considering these groups in isolation. What happens with the interactions between them?
What happens is I don't understand. What is the problem? Even if they are interacting, this statement is true. What is the statement? I'm writing the statement very clearly, okay? The statement is, if X is in S minus M, if XAB forms a group, then this implies that A and B is in M. Now, A and B are not fixed students. X is also not a fixed element, not a fixed student outside M. Take any student outside M. If that form any group, then the other 2 members of the group must be included in M.
Oh, okay.
That is the statement.
Let me go through your argument. B belongs to M. Why? Because if A and B, suppose A does not belong to M. What happens then?
Yeah.
You can add X to M, and there will be no problem.
There will be no problem, but that is a problem. That there is no problem.
Yeah,
that is a problem because M was maximal.
Yeah, there will be no problem.
Yeah.
But suppose XCD is a group and CD are already in M, C and D are already in M. Now, if you add X to that group, it will be a problem.
Okay. Yeah.
That is the stoppage in the argument. That is the problem in the argument. That's what I'm saying.
Yeah, that is fine. That is fine. So, so what you are saying here? You are saying that, but then there is CD in M, right? Okay, I understand your point. Yeah. Fine.
So
fine,
any
fine,
group
fine,
with X will does not mean that the other 2 are there. There
exactly.
is at least one group which happens.
There is yeah. Very nicely pointed out. Yeah. Exactly. So this is kind of the first group we are starting with, in some sense. Now is it fine? If AB is not in M, then there is some CD which is in M and where this is satisfied. Okay, yeah, fine. But that doesn't make it. The point is true, but still we can define a function like this, right?
Yeah, could you go through why? How do you define the function? Like suppose
We
x,
just
AB,
map
x.
x to AB.
Huh.
Yeah,
Yeah.
so let me just define a function here.
So what is A and
So
what is B?
A and B are the two students in some group of X, which is in M.
So how
Like
do you decide
for
which
X not to, so just let me give a there exist here, okay? Because that is the thing you pointed out, right?
Yeah.
The thing is for X to be outside M, for X to be outside M, there must be a reason for which we can't include X in M. And that reason is boiling down to two other students forming a group with X, and that two students already being in M.
Oh, so that is that is why John's lemma is required, right? Axiom of choice. You have to...
Yeah. That is why we need the maximality. Now, how to define the function? We define the function in this way. We take S minus M to all the two subsets of M. The two subsets of M means like M1, M2. Sorry. M1, M2. M1, M2. M1 not equal to M. Okay. This is the set of two subsets. Set of two subsets. Two subsets means subsets of coordinated in M. Okay. How do we map that? We map X mapping to AB, where XAB forms a group, and as you pointed out, we need to mention and AB is in M. And what we discussed about it before is there exists such a group belonging X such that the other two students are already in M. Now is it clear? Now is it fine? I don't know who was asked. Yeah, it is clear, right? Very good. Yeah, so very nicely pointed out. Yeah, thanks for that. Yeah, so now you see, now what is the cardinality of this thing? That is M choose 2. The cardinality of M choose 2. Now, sorry, we talked about injectivity here, right? And there is a problem with injectivity. If Fy is not equal to Fz, Y not equal to Z. If Fy is equal to Fz, Y not equal to Z, then YAB and ZAB are two groups with more than one element in common, which is not possible because of our hypothesis. So if Y is not equal to Fz, whenever Y is not equal to Z. So the map is injective, and injective map means that, what does that mean? It means, tell me, if this is a map injective from A to B, A and B both are finite sets, then what do we get? What do we get? Tell me the cardinality of this thing first. Anyone? This is a very fundamental thing. If F is an injective function from A to B and A, B both are finite sets, then what can one say about the
B greater than equal to A, cardinality.
Yeah, exactly. Cardinality of B is greater than equal to cardinality of A. So what about here? Here the cardinality of B is cardinality of M choose 2, which is greater than equal to cardinality of S minus M. Now what is S? This says, let's say the number of elements is M, small m choose 2 is greater than equal to 46 minus M. Because number of students is 46, right? So now just solve the equation. N minus M2 sorry, it's greater than equal to 6 minus n. Now do something. I don't know, something you can do, and this will simplify and give you this thing, right? That in this will it should the set.
So you see that this so m square plus m by 2, I think what will happen is that for 9, m equal to 9, it will be less than 46, and for 10, it will be greater than 46. That's why.
Yeah. So something like that, and you will get, yeah. So that you can just figure it out. Yeah. So see, again, the fundamental thing of understanding is defining functions between two sets in order to tell something about the cardinality of the two sets. And not only that, and also about talking about the existential things in F by defining the function in such a way that we did in the previous talk. So these are the very fundamental uses of functions, and they are very interesting, like very, very interesting. You can look at, like, see many more examples on books or whatever. So I think, yeah, we also have to discuss probability. Now, probability, you can, like, probability is a huge thing. Firstly, that is the thing. Probability, combinatorics is a very smaller branch than probability is. But what we do in 10+2, in front exam or whatever the MCQ problem type is generally combinatorial probability. That is just probability of finite sets where all the thing you need to know probability is probability of an event is the number of ways the event can happen divided by the sample size. Both are finite. So just do that. And that is just counting the number of ways the event can happen. And then there is that base formula and stuff like that. Condition and probability formula. All these are very, very technical stuff. But what is the beauty of probability, which you might use in some combinatorics problem also, is using random variables and then expectations and variance, inequalities using that. All these are very important. Then graphs, they are also very useful in solving advanced problems. So maybe, I don't know, like before ISI exam, it's not much of use to study that. But I can, if you are interested, just ping me. I can send you a bunch of notes on probabilistic use of combinatorics, if you can say so. Okay, so I think that's it for today. If there is any doubt, let me know. Otherwise, that's it. Okay then, all the best for your exams and good night.